Hello and welcome to Bedtime Science. Before we begin, take a moment to like the video, subscribe to the channel, and let me know in the comments where you're watching or listening from tonight. Whether it's a quiet room on Earth, under a city sky, or somewhere far away where the stars feel just a little closer. Because wherever you are already part of this story. Tonight, we're going to explore a question that reaches further than any distance you could ever travel. A question that quietly sits behind everything you've ever seen, felt, or known. What actually started the universe? Not just how it grew, not just how it looks today, but what began it all. And as we begin, it helps to let go of one very common image. There was no explosion into empty space, no fireball bursting outward into darkness. Instead, space itself was once compressed into an incredibly hot, dense state, and then, slowly, silently, it began to expand. Every galaxy, every star, every atom, even the space between them, all stretching outward together. The room you're in right now, the air around you, even the distance between distant galaxies, all part of that same ongoing expansion. And the remarkable thing is, we can actually see the evidence. We can observe galaxies drifting away from one another. We can detect a faint glow of ancient radiation, still echoing from the early universe. We can measure the exact ingredients of matter that are formed in those first moments. It's as if the universe has left behind a quiet trail, a set of clues, allowing us to gently reconstruct its history. But the deeper we look, the more subtle the question becomes. Because while the Big Bang explains how the universe began expanding, it doesn't fully explain why it began at all. Was there a moment before the beginning? Could the universe have emerged from something deeper, something stranger than space and time? Or could the very idea of a beginning be something our minds are not quite built to understand? Tonight, we'll explore all of this, slowly, carefully, moving from what we can observe to what we can infer, and finally, to the edge of what we may never fully know. So as you settle in, let your thoughts drift outward, because the story of the universe is also, quietly, the story of where you are right now. Some questions feel distant, almost abstract, like they belong to philosophers or late-night conversations that drift away before they find an answer. And then there are questions that are so simple, so fundamental, that they quietly sit underneath everything else. What actually started the universe? It is a question that sounds almost childlike at first, the kind of thing someone might ask while looking up at the night sky for the first time. But the more you sit with it, the more it begins to unfold into something much deeper. Because this is not just a question about distant galaxies, or ancient light, or the edge of space. It is a question about where everything came from. Every star, every planet, every atom in your body, even the space around you, the very stage on which reality plays out, has a history. And yet, for most of human history, we had no reliable way to answer this question scientifically. For thousands of years, people turned to stories, traditions, yes, and philosophical ideas to explain the origin of the universe. Some imagined cosmic eggs, others described cycles of creation and destruction, and many traditions spoke of beginnings shaped by unseen forces or divine intentions. These ideas were meaningful, and often beautiful, but they were not built on observation or measurement. Modern science takes a different approach. Instead of asking what sounds right, or what feels meaningful, science asks a quieter question. What can we actually observe? What can we measure, test, and verify? This shift in thinking, from storytelling to evidence, is what eventually gave rise to a field known as cosmology. Cosmology is the scientific study of the universe as a whole, its origin, its structure, and how it changes over time. And unlike many areas of science, cosmology deals with scales that are almost impossible to imagine. The observable universe is estimated to span about 93 billion light years across. A single light year, just one, is the distance light travels in a year, moving at nearly 300,000 kilometers every second. That means even the smallest measurements in cosmology involve distances so vast that numbers alone begin to lose their meaning. And yet, despite this enormous scale, scientists have found ways to study it. They use telescopes to observe distant galaxies. They measure faint signals left over from the early universe. They analyze the distribution of matter across space, and slowly, piece by piece, a picture begins to emerge. Not a perfect picture, not a complete one, but one that is grounded in evidence. Now, one of the most important ideas in cosmology is that the universe is not static. It is not unchanging or fixed in place. Instead, it evolves. It has a history, and if something has a history, it suggests that it may also have had a beginning. But here is where the question becomes more subtle. When we ask what started the universe, we're not just asking about an event. We're asking about the origin of space itself, the origin of time, the origin of the laws that govern everything we observe. This makes the question very different from everyday questions. If you ask what started a fire, you can trace it back to a spark. If you ask what started a river, you can follow it to a source. But when you ask what started the universe, you're asking about the source of everything, including the concepts you would normally use to describe a source. This is where science and philosophy begin to overlap, but they do not become the same thing. Science remains focused on what can be observed and tested. It builds models, makes predictions, and checks those predictions against reality. Philosophy, on the other hand, often explores questions that may not have direct observational answers. Both approaches can be valuable, but in this journey, we will stay grounded in what science can tell us, while still acknowledging where its limits begin. And those limits are important, because as we move closer to the earliest moments of the universe, our current theories begin to stretch. The laws of physics that work so well in everyday situations, and even in the behavior of stars and galaxies, may not fully apply under the extreme conditions of the very beginning. Temperatures would have been unimaginably high, densities far beyond anything we can recreate in experiments. In those conditions, our understanding becomes less certain, but uncertainty does not mean we know nothing. In fact, one of the most remarkable achievements of modern science is that we can say quite a lot about the early universe with surprising confidence. We know that it was once much hotter, much denser, much more uniform than it is today. We know that it has been expanding over time, and we know this not from guesswork, but from multiple independent lines of evidence. Evidence that we will explore slowly, piece by piece. As we move forward, the journey will unfold in layers. We will begin with what we can directly observe, such as the motion of galaxies and the faint radiation that fills all of space. From there, we will step into the models that explain those observations, including the idea known as the Big Bang, and eventually, we will reach the edges of current knowledge, where scientists are exploring more speculative ideas about what might have come before, or whether that question even makes sense. There is no need to rush. These ideas have taken decades, even centuries, to develop, so we can take our time with them. Let the concepts settle. Let the scale of things unfold gradually. Because understanding the universe is not about arriving quickly at an answer. It is about slowly building a picture, one that becomes clearer, and at the same time, more mysterious. And perhaps that is part of what makes this question so enduring. The more we learn about the universe, the more we realize how much there is still to understand. And yet, even within that uncertainty, there is something quietly reassuring. Because the same laws of physics that describe distant galaxies also describe the atoms in your body. The same story that explains the expansion of the universe also explains how stars form, how elements are created, and how planets like Earth come into being. So when we ask what started the universe, we're not just asking about something far away, we're asking about the beginning of everything that eventually led to here, to this moment, to this question, to you. And as we continue, we will begin to see how science has approached this question, not with certainty, but with careful observation, thoughtful models, and a quiet willingness to follow the evidence wherever it leads. Time feels simple, at least at first. It moves forward. It gives structure to our days. It allows things to change, to age, to unfold. We measure it with clocks, divide it into seconds, minutes, and hours, and use it to organize everything from daily routines to the motion of planets. But when physics looks more closely, time becomes something far less straightforward. It is not just a background ticking away behind the universe. It is part of the universe itself. And understanding that shift from time as something external to time as something woven into reality is essential if we want to understand how the universe began. For a long time, time was treated as absolute. In the view developed by Isaac Newton in the late 17th century, time flowed at a constant rate everywhere, independent of anything else. It was the same for every observer, unaffected by motion, gravity, or location. This idea worked remarkably well for everyday situations. It allowed scientists to describe motion, forces, and planetary orbits with great accuracy. But as measurements became more precise, and as new phenomena were explored, cracks began to appear. The turning point came in the early 20th century, when Albert Einstein introduced a radically different way of thinking. In 1905, Einstein developed the theory of special relativity, showing that time is not the same for everyone. If two observers are moving relative to one another, they will measure time differently. Clocks in motion tick more slowly compared to clocks at rest. This effect, known as time dilation, has been confirmed in countless experiments, including precise measurements using atomic clocks on airplanes and satellites. But Einstein did not stop there. In 1915, he presented general relativity, a theory that goes even deeper. Instead of treating gravity as a force acting at a distance, general relativity describes gravity as the curvature of space-time, and this is where things become especially important. Space-time, not space, and time separately, but a single, unified structure. In this framework, space and time are woven together into a four-dimensional fabric. Objects move through space-time, and massive objects like stars and galaxies cause that fabric to curve. This curvature is what we experience as gravity, and just as motion can affect time, so can gravity. The stronger the gravitational field, the slower time passes. Near a massive object such as a neutron star or a black hole, time can slow dramatically compared to regions farther away. This is not just theoretical. Experiments have measured time passing at slightly different rates at different altitudes on Earth. Even the Global Positioning System, the network of satellites that allows your phone to determine its location, must account for these relativistic effects to remain accurate. So time is not universal, it is not constant. It is flexible, shaped by motion and gravity, and once we accept that, another idea begins to emerge. If time is part of space-time, and space-time itself can change, then time may also have a beginning. This is where the question becomes more subtle. When we ask what happened before the universe, we're assuming that time existed before the universe began. But if time itself is part of the universe, then asking what came before, it may not be meaningful in the usual sense. It is a bit like asking what is north of the North Pole. The question sounds reasonable, but it depends on a framework that no longer applies at that boundary. In the case of the universe, general relativity suggests that if we trace cosmic history backward, we reach a point where density and curvature become extreme. This idea is often referred to as a singularity, a state where the known laws of physics, as described by general relativity, break down. It does not necessarily mean that everything was compressed into a single point in a simple way. Rather, it indicates that our current mathematical descriptions are no longer sufficient. But within that framework, time itself appears to emerge along with the expansion of the universe. In other words, time does not extend infinitely into the past. Instead, it has a finite history. Modern cosmological models estimate that the observable universe has been expanding for about 13.8 billion years. That number is not arbitrary. It comes from multiple lines of evidence, including measurements of cosmic expansion, observations of the cosmic microwave background, and detailed models of how the universe has evolved. But more important than the number itself is what it implies. If time has a finite duration, then the universe is not just evolving within time. Time itself is evolving with the universe. This idea can feel difficult to grasp, because our everyday experience is built around time as something constant and ever-present. We remember the past, we anticipate the future, and we live in a continuous flow of moments. But at the scale of the universe, time behaves differently. It is tied to the structure of space-time, and that structure has changed dramatically over cosmic history. There are even theoretical models that explore how time behaves near the beginning. One example is the Hartle-Hawking no-boundary proposal, developed by James Hartle and Stephen Hawking. In this model, time near the beginning of the universe behaves more like a spatial dimension. Instead of a sharp starting point, the universe transitions smoothly, without a distinct boundary in time. It is a bit like the surface of the Earth. You can travel north until you reach the North Pole, but there is no edge or boundary where the surface suddenly ends. In a similar way, the beginning of the universe may not be a moment in time, but a region where our usual concept of time changes its meaning. This does not mean that all questions disappear. It simply means that some questions need to be reframed. Instead of asking what happened before the universe, scientists often ask how space-time itself behaves under extreme conditions. What laws govern it? How does it emerge? And how does it evolve into the universe we observe today? These are questions that can be approached with observation, mathematics, and theory. And while the answers are not yet complete, they have already transformed our understanding. So when we think about the beginning of the universe, it is not just a story about matter and energy. It is also a story about time itself, a story in which time is not the stage, but part of the unfolding event. And as we continue to explore this idea, it becomes clear that understanding the origin of the universe requires us to rethink some of our most basic assumptions, because the beginning of everything may also be the beginning of time. The phrase Big Bang has a way of planting a very specific image in the mind, a sudden explosion, a burst of light and energy tearing outward into empty space, a single point igniting and sending everything flying in all directions. It is dramatic, it is memorable, and it is not quite right. Because the Big Bang was not an explosion in space, it was the expansion of space itself. That distinction may sound subtle at first, but it changes everything. To understand why, it helps to step away from familiar experiences. When we think of an explosion, we imagine something happening within space. A firework expands into the air. A supernova throws material outward into the surrounding vacuum. In both cases, there is already a space for the explosion to expand into. But the Big Bang is different. There was no pre-existing empty space waiting to be filled. Instead, space itself was once in an extremely hot, dense state, and then it began to expand. Not outward into anything, but everywhere at once. This idea was first developed in a scientific form by Georges Lemaître, a Belgian physicist and priest in the late 1920s. Lemaître proposed that the universe began from what he called a primeval atom. This was not an atom in the everyday sense, not something made of protons and electrons, but rather a way of describing a universe that was once compressed into an incredibly small, dense state. From that state, space expanded, and as it expanded, it cooled, and as it cooled, matter began to form. At the time, this idea was unusual, even controversial. Many scientists believed the universe was static, unchanging on large scales. But Lemaître's work provided a framework that would soon be supported by observation. Still, even today, the language we use can lead to confusion. One of the most common misunderstandings is the idea that the Big Bang happened at a specific point in space, a kind of central location from which everything moved outward. But in modern cosmology, there is no central point. Every location in the universe can be considered the center, because the expansion happens everywhere. A helpful way to picture this, gently, is with the surface of a balloon. Imagine a balloon with small dots drawn on its surface. As the balloon inflates, the surface expands. Each dot moves away from every other dot, and from the perspective of any single dot, it appears as though all the others are moving away. But there is no special center on the surface itself. The center of the balloon exists in a higher dimension, not on the surface where the dots live. In a similar way, the expansion of the universe does not require a central point within the universe. Every region of space expands relative to every other region. Now, the balloon analogy is not perfect. The universe is not expanding into a higher dimensional space in any simple sense, and it is not a two-dimensional surface. But the analogy captures something important. Expansion does not need a center within the system being described. Another common misconception is the idea that galaxies are moving through space away from a central origin, like debris from an explosion. In reality, what we observe is something more subtle. The galaxies are not simply flying through space. The space between them is stretching. As space expands, the distance between galaxies increases, even if the galaxies themselves are not moving through space in the usual sense. This leads to a key observational effect known as redshift. When light travels through expanding space, its wavelength stretches along with that space. As a result, the light shifts toward the red end of the spectrum. This effect was observed by Edwin Hubble in the 1920s using the telescope at Mount Wilson Observatory. Hubble found that distant galaxies appear to be moving away from us, and that the farther away a galaxy is, the faster it appears to recede. This relationship is now known as Hubble's law. It can be described in words as follows. The recessional velocity of a galaxy equals the Hubble constant multiplied by its distance from the observer. This is not just a curious observation. It is a direct consequence of expanding space, and it provides one of the strongest pieces of evidence for the Big Bang model. If the universe is expanding today, then in the past it must have been smaller, hotter, denser. And if we follow that logic far enough, we arrive at a state where everything was compressed into an extremely dense energetic condition. Not an explosion, but an expansion from that state. Another way to think about this is to imagine reversing the expansion. If galaxies are moving away from each other now, then going backward in time, they must have been closer together, closer still, and closer still, until the distances between them become extremely small. This is not just a thought experiment. It is a mathematical consequence of the equations of general relativity when applied to a universe that is expanding. And importantly, this expansion happens everywhere. There is no edge where the expansion stops, no boundary where space suddenly ends. As far as observations can tell, the universe is either infinite or so large that any edge lies far beyond what we can detect. This idea can feel counterintuitive. In everyday life, we are used to objects having edges, boundaries, limits. But space itself may not behave that way. Instead, it can expand without needing to expand into anything. That is perhaps one of the most unusual aspects of the Big Bang. It challenges our intuition, not because it is illogical, but because it operates on scales and conditions far removed from everyday experience. And yet, despite how strange it may sound, the model makes precise predictions. It predicts that galaxies should be moving away from each other. It predicts that the universe should have been hotter in the past. It predicts that there should be remnants of that early hot state, still observable today. And as we will see, those predictions have been confirmed in multiple independent ways. So when we speak of the Big Bang, it is helpful to gently set aside the image of an explosion. Instead, we can think of it as the beginning of expansion, a moment, or perhaps a phase, when space itself began to stretch, carrying everything within it along for the journey. No center, no edge, no explosion into emptiness, just a universe, expanding, everywhere, all at once. And in that quiet expansion, the entire history of the cosmos begins to unfold. At the beginning of the 20th century, the universe was often imagined as something still and unchanging. A vast, quiet backdrop where stars and galaxies simply existed, fixed in place, eternal and steady. It was a comforting picture. Nothing too dramatic, nothing too dynamic. But as telescopes improved and as measurements became more precise, that calm image began to shift, and one of the key figures in that shift was Edwin Hubble. Working at Mount Wilson Observatory in California, Hubble had access to one of the most powerful telescopes of his time, the Hooker telescope, with a mirror 100 inches across. By today's standards, that might sound modest. But in the 1920s, it was a remarkable instrument. With it, Hubble was able to observe distant objects that had previously appeared as faint, unresolved smudges. At the time, there was still debate about what those smudges actually were. Some scientists believed they were part of our own galaxy, the Milky Way. Others suspected they might be entirely separate systems, vast collections of stars far beyond our own. Hubble's observations helped resolve that question. By studying a type of star known as a Cepheid variable, whose brightness changes in a predictable way, he was able to estimate distances to these objects, and what he found was astonishing. These nebulae were not nearby at all. They were entire galaxies, far outside the Milky Way, separated by enormous distances. The universe suddenly became much larger than previously imagined. But that was only the beginning, and around the same time another astronomer, Vesto Slipher, had been measuring the spectra of galaxies. When light from an object is spread out into a spectrum, much like a rainbow, it reveals patterns that correspond to specific elements. These patterns act like fingerprints, and importantly, they can shift. If an object is moving toward us, its light shifts toward shorter wavelengths, appearing slightly bluer. If it is moving away, the light shifts toward longer wavelengths, appearing redder. This effect is known as the Doppler shift. Slipher found that most galaxies showed a redshift. Their light was stretched, shifted toward the red end of the spectrum. This suggested that they were moving away from us. Hubble combined these redshift measurements with his distance estimates, and what he discovered was something remarkably simple and profoundly important. The farther away a galaxy is, the greater its redshift. In other words, the more distant the galaxy, the faster it appears to be moving away. This relationship became known as Hubble's law, and in clear terms it can be expressed as the velocity at which a galaxy moves away is equal to the Hubble constant multiplied by its distance. This is not just a pattern in the data, it is a direct signature of an expanding universe, because if space itself is stretching, then the farther apart two galaxies are, the more space there is between them to expand, and so their separation increases more rapidly. It is a bit like markings on a stretching piece of fabric. If the fabric expands evenly, points that are farther apart will move away from each other faster than points that are close together, not because they are moving through the fabric, but because the fabric itself is stretching, and this stretching affects the light travelling through it. As light moves across expanding space, its wavelength increases. It becomes stretched, just like the space it is travelling through. This is what we observe as redshift. It is not simply a matter of galaxies flying away like particles in an explosion. It is the space between them growing. This distinction is subtle, but it is crucial, and it leads to a powerful realization. If the universe is expanding now, then in the past it must have been smaller. If galaxies are moving away from each other today, then earlier in time, they must have been closer together. And if we continue to trace this backward, the universe becomes denser, hotter, and more compact. This idea does not rely on imagination alone. It comes directly from observation, from measurements of light, from the behavior of galaxies, and it provides a way to reconstruct cosmic history, not by guessing, but by following the evidence. It is almost like watching a film in reverse. Instead of seeing galaxies drift apart, we imagine them moving closer together. Instead of space stretching, we imagine it contracting. And as we continue this mental reversal, the universe approaches a state where distances become extremely small, where temperatures rise dramatically, where matter and radiation are packed into an intense energetic environment. Of course, this process cannot be extended indefinitely without limits. At some point, our current theories reach conditions where they're no longer fully reliable. But up to that point, the picture is remarkably consistent. Independent observations all point in the same direction. The universe has been expanding, and that expansion implies a very different past. It is also worth noting that this expansion is not something we feel directly, on human scales, or even within galaxies. Gravity and other forces hold structures together. The Earth does not drift away from the Sun. The solar system does not dissolve. The Milky Way does not stretch apart. Expansion becomes noticeable only on the larger scales, between galaxies separated by vast distances. This can make the concept feel distant, almost abstract. But the evidence is clear. Every time we observe distant galaxies, every time we measure their light, we are seeing the imprint of expansion. And this discovery, made nearly a century ago, continues to shape our understanding of the universe. It transformed cosmology from a largely speculative field into a data-driven science. It provided a foundation, a starting point, for everything that followed. Because once you accept that the universe is expanding, a natural question arises. What happens if we keep going backward? What happens if we continue to rewind, further and further, toward the earliest possible moment? This is where observation begins to meet theory, where data leads to deeper questions, and where the story of the universe begins to take on a new direction. Not just a universe that exists, but a universe that changes, and one that, in some sense, had a beginning. If the universe is expanding today, then it carries within it a quiet record of its past, not written in words, but encoded in motion, in light, in the distribution of a matter across vast distances. And by carefully studying those clues, scientists have learned how to reconstruct what the universe was like long before there were galaxies, long before there were stars, even long before there were atoms. This process is not guesswork. It is based on a simple but powerful idea. If you understand how something behaves now, and you understand the laws that govern it, then you can, in principle, trace that behavior backward in time. This approach is sometimes called extrapolation. In cosmology, it means taking the observed expansion of the universe and running the equations of physics in reverse. As we do this, a clear pattern begins to emerge. The universe becomes smaller, distances between galaxies shrink. And as those distances decrease, something else happens as well. The density of matter increases. Density in this context simply means how much mass is contained within a given volume of space. If you compress the same amount of matter into a smaller volume, the density rises. This is not unique to cosmology. It is something we experience in everyday situations. If you take a gas and compress it into a smaller container, the particles become more crowded. They collide more frequently. And as a result, the temperature tends to increase. The same general principle applies to the universe as a whole, but as we move backward in time, the universe becomes denser and hotter, not gradually, but dramatically. At early stages, temperatures would have been far beyond anything we encounter in daily life. For comparison, the surface of the Sun is about 5,500 degrees Celsius. In the early universe, temperatures reached billions, even trillions of degrees. At such extreme conditions, matter behaves very differently. Atoms cannot exist. Electrons are not bound to nuclei. Instead, matter exists as a plasma, a hot, dense mixture of charged particles and radiation. And if we go even further back, to earlier and earlier times, the energy becomes so intense that even protons and neutrons cannot hold together. The universe becomes a sea of fundamental particles, interacting in ways that are described by high-energy physics. To model these conditions, cosmologists rely on well-tested theories. General relativity describes how space-time evolves under gravity. Quantum field theory describes how particles behave at very small scales and high energies. By combining these frameworks, scientists can construct models of the early universe that are remarkably detailed. This is why cosmology is often described as a reconstructive science. Unlike laboratory sciences, where experiments can be repeated and controlled, cosmology studies a single system, the universe itself. We cannot recreate the entire universe in a laboratory, but we can observe it, measure it, and use those observations to infer its history. In a sense, the universe acts as its own experiment, and we are reading the results. One of the key tools in this reconstruction is the set of equations derived from general relativity, known as the Friedmann equations, developed by Alexander Friedmann in the 1920s. These equations describe how the expansion of the universe changes over time, depending on factors such as density, pressure, and the overall curvature of space. In words, one of these relationships can be expressed as follows. The rate at which the universe expands depends on the total energy density contained within it. This includes matter, radiation, and other components such as dark energy. By measuring the current expansion rate and estimating the density of these components, scientists can calculate how the universe must have evolved in the past. And when they do, the results consistently point toward a hot, dense, early state. This is not based on a single line of reasoning. It is supported by multiple independent observations, the expansion of galaxies, the background radiation that fills space, the abundance of light elements. Each of these provides a different window into the early universe, and importantly, they all tell a consistent story. But as we continue to move backward, pushing our models closer to the earlier moments, we begin to encounter limits. Not limits of curiosity, but limits of our current understanding. At extremely high energies, the known laws of physics begin to break down. General relativity, which describes gravity on large scales, does not fully incorporate quantum effects. Quantum mechanics, which governs the behavior of particles, does not fully describe gravity. And at the earliest times, both effects are important. This is where the need for a theory of quantum gravity arises, a framework that can unify general relativity and quantum mechanics into a single, consistent description. Despite decades of research, such a theory is not yet complete. There are promising approaches, such as string theory and loop quantum gravity, but no definitive answer. As a result, When we approach what is known as the Planck time, approximately 10 to the power of minus 43 seconds after the beginning of expansion, our models become uncertain. To give a sense of scale, this is a fraction of a second so small that it is difficult to compare it to anything familiar. If 1 second were expanded to the age of the universe, the Planck time would still be unimaginably brief. Beyond this point, our current equations no longer provide reliable predictions. This does not mean that nothing happened. It simply means that we do not yet have the tools to describe it fully. And this is an important distinction. Science does not claim certainty where it does not exist. Instead, it identifies the boundaries of knowledge and works to extend them. So as we reconstruct the early universe, we move with confidence through certain eras and with increasing caution as we approach the limits of current theory. This layered understanding is one of the strengths of modern cosmology. It does not rely on a single idea, but on a network of interconnected evidence and models. Each piece supports the others, each adds clarity, and together they form a coherent picture of cosmic history. A picture that begins not with an explosion into space, but with a universe that was once far more compact, far more energetic, and very different from what we see today. And as we continue to explore this history, we will begin to examine the specific evidence that supports it. Not just the expansion of galaxies, but the faint glow of ancient radiation and the precise composition of matter itself. Clues that have been travelling across billions of years, quietly carrying the story of the universe's earliest moments, waiting to be understood. If the early universe was once incredibly hot, dense, and filled with energy, then it should have left something behind. Not a dramatic signal, not a sharp edge or a visible boundary, but something quieter. A faint trace, spread evenly across the sky, carrying with it a memory of those earliest conditions, and that is exactly what scientists discovered. It is known as the cosmic microwave background, often shortened to the CMB. It is not something you can see with your eyes. It does not glow in the way stars do, but it is everywhere, in every direction, filling all of space. There's a faint background radiation, a kind of afterglow from the early universe. To understand where it comes from, it helps to imagine what the universe was like when it was much younger. In its earlier stages, the universe was so hot that matter could not exist in the form we are familiar with. Atoms could not hold together. Electrons and protons moved freely in a dense, energetic plasma. In this state, light could not travel far. Photons, which are particles of light constantly scattered off charged particles, changing direction again and again. The universe was, in a sense, opaque, not dark, but more like a glowing fog, where light could not move freely. As the universe expanded, it cooled, and after about 380,000 years, something important happened. The temperature dropped to around 3,000 degrees Celsius. At this point, electrons and protons were able to combine to form neutral hydrogen atoms. This process is known as recombination, although it is actually the first time these atoms formed. Once atoms formed, the universe changed dramatically. Photons were no longer constantly scattered. They could travel freely through space. The universe became transparent, and the light that was released at that moment has been travelling ever since. That light is what we now observe as the cosmic microwave background, but it does not appear today as bright, visible light. over billions of years, as the universe expanded, the wavelengths of that light stretched. What was once high-energy radiation has been shifted into the microwave region of the electromagnetic spectrum. Today, the cosmic microwave background has a temperature of about 2.7 degrees above absolute zero. That is extremely cold, just a few degrees warmer than the coldest possible temperature, and yet it is remarkably uniform. No matter where we look in the sky, this background radiation is present, with almost the same temperature in every direction. The discovery of this radiation was not originally planned. In the early 1960s, Arno Penzias and Robert Wilson were working at Bell Laboratories in New Jersey. They were using a sensitive radio antenna designed for satellite communication experiments. But as they calibrated their equipment, they encountered a persistent noise, a faint signal, coming from every direction. They checked their instruments. They accounted for known sources of interference. At one point, they even cleaned out the antenna, removing what they described as white dielectric material, which is a polite way of referring to bird droppings. And yet, the noise remained, unchanging, uniform, always present. At the same time, a group of physicists at Princeton University, including Robert Dick and Jim Peebles, were working on theoretical predictions, and they had calculated that if the universe had once been hot and dense, there should be a leftover background radiation, cooled by expansion, still detectable today. When Penzias and Wilson learned of this work, the pieces fell into place. The signal they had detected was not noise, it was the afterglow of the early universe. This discovery provided one of the strongest pieces of evidence for the Big Bang model. It showed that the universe had indeed passed through a hot, dense phase. And importantly, it provided a direct window into that early time. Since then, the cosmic microwave background has been studied in extraordinary detail. In the late 1980s and early 1990s, the Cosmic Background Explorer, or COBE mission, led by NASA, made the first precise measurements of this radiation. COBE confirmed that the spectrum of the CMB matches that of a nearly perfect blackbody, meaning it has the exact distribution of wavelengths expected from an object in thermal equilibrium. In simple terms, this is exactly what you would expect from a universe that was once hot and uniform. But COBE also revealed something even more intriguing. Tiny variations in temperature, differences of only a few parts in 100,000, almost perfectly smooth, but not completely. These small fluctuations were later mapped in greater detail by the Wilkinson Microwave Anisotropy Probe, known as WMAP, and then with even higher precision by the Planck satellite, a mission of the European Space Agency. These missions produced detailed maps of the early universe, showing slight variations in temperature across the sky. At first glance, these variations might seem insignificant, but they are crucial because they represent tiny differences in density in the early universe, regions that were slightly denser and regions that were slightly less dense. Over time, gravity amplified these differences. Denser regions pulled in more matter, less dense regions remained more sparse, and gradually, over hundreds of millions and billions of years, these small fluctuations grew into the large-scale structures we see today. Galaxies, clusters of galaxies, filaments of matter stretching across vast distances. In other words, the cosmic microwave background does not just tell us that the universe was once hot and uniform. It also contains the seeds of everything that came later. It is a snapshot of the universe at a very early stage, before stars, before galaxies, before complex structures, a moment when the universe was simple, but not perfectly smooth, and those tiny imperfections, those slight variations, made all the difference. Without them, matter would not have clumped together. There would be no galaxies, no stars, no planets, and perhaps no observers to wonder about it. So in a very real sense, the cosmic microwave background is not just a relic of the past. It is a key part of the story of how the universe became what it is today, and what makes it especially remarkable is that it is still here. Every time a radio telescope scans the sky, it detects this faint glow, a signal that has been travelling for billions of years, largely unchanged, carrying information from a time when the universe was only a few 100,000 years old. It is one of the oldest things we can observe, a quiet, persistent reminder that the universe has a history, and thus the careful observation, even the faintest signals, can reveal the deepest truths. Long before the first stars began to shine, before galaxies gathered into vast clusters, the universe was already beginning to assemble the simplest ingredients of matter. Not atoms as we know them today, not yet, but the building blocks that would eventually make atoms possible. This process is known as Big Bang nucleosynthesis. The term may sound complex, but at its core it describes something quite straightforward. It is the formation of the universe's first atomic nuclei in the earliest moments after expansion began. To understand how this happened, we need to return to a time when the universe was still incredibly hot. Not just hot in the everyday sense, but so hot that ordinary structures could not exist. In the first few seconds, temperatures were measured in billions of degrees. At these energies, particles collided constantly, breaking apart and reforming in a dense, energetic environment. Protons and neutrons, the components of atomic nuclei, existed freely, moving through this intense sea of energy. But conditions were not stable. There was a delicate balance between processes that created neutrons and those that caused them to decay. As the universe expanded, it cooled, and as it cooled, the balance began to shift. Neutrons are slightly more massive than protons, and they are not stable on their own over long periods. So as time passed, some neutrons decayed into protons. This meant that by the time nucleosynthesis began in earnest, there were more protons than neutrons. This ratio would turn out to be very important, because when nuclei began to form, they did so based on what was available. The simplest nucleus is hydrogen, which consists of a single proton, and because protons were more abundant, hydrogen became the most common element in the universe. But under the right conditions, protons and neutrons could combine. When a proton and a neutron bind together, they form a nucleus known as deuterium, a heavier form of hydrogen. From there, further combinations become possible, and 2 protons and 2 neutrons can form helium, one of the most stable and abundant elements. A small amount of lithium can also form through more complex interactions, although in much smaller quantities. This entire process occurred within the first few minutes of cosmic history, not hours, not years, but minutes. After that, the universe expanded and cooled to the point where nuclear reactions could no longer proceed efficiently. In a sense, nucleosynthesis came to a natural stop. the universe was left with a very specific mixture of elements. Roughly speaking, about 75% hydrogen, about 25% helium, and trace amounts of lithium. These percentages are not exact, but they are remarkably consistent across observations, and this is where things become especially interesting. And because these proportions were not simply measured after the fact, they were predicted. In the 1940s, physicist George Gamow, along with collaborators Ralph Alpher and Robert Herman, developed early models of nucleosynthesis in a hot, expanding universe. They calculated how nuclear reactions would proceed under those conditions. They estimated how much hydrogen and helium should form, and their predictions were clear. If the universe began in a hot, dense state, then it should contain a specific ratio of light elements. This was not a vague idea. It was a testable prediction. And when astronomers later measured the composition of the universe, particularly in ancient gas clouds and distant regions that had not been heavily altered by stars, they found something remarkable. The observed abundances matched the predictions. Hydrogen was dominant. Helium was present in significant amounts, about 1/4 of the total mass. Lithium appeared in small quantities. This agreement between theory and observation is one of the strongest pieces of evidence supporting the Big Bang model, because it shows that the model does not just describe the expansion of the universe, it also correctly predicts the outcome of physical processes that occurred in its earliest moments. And importantly, these processes are based on well-understood physics, nuclear reactions, particle interactions, thermodynamics, the same principles that are tested in laboratories and observed in stars. There is even a helpful comparison that can make this more intuitive. Stars, like our Sun, also produce elements through nuclear fusion. Either they take hydrogen and convert it into helium over long periods of time. But stars operate under very different conditions. They are localized, relatively stable, and evolve over millions or billions of years. Big Bang nucleosynthesis, by contrast, happened everywhere at once, and within a very short window of time. The entire universe acted as a kind of cosmic furnace, briefly hot enough to fuse nuclei before cooling too quickly for heavier elements to form. That is why elements like carbon, oxygen, and iron, which are essential for life, were not created during this early phase. They were formed later, inside stars, and distributed through processes like supernova explosions. So the elements produced in Big Bang nucleosynthesis are the simplest ones, but they are also the most abundant. Hydrogen, in particular, remains the dominant element in the universe. It fuels stars, it forms gas clouds, it plays a central role in the structure and evolution of galaxies, and helium. The second most abundant element is also a direct product of those early moments. Together, they form the foundation upon which everything else is built. There is, however, one small detail that continues to be studied. The amount of lithium observed in some regions of the universe is slightly lower than what the simplest models predict. This discrepancy is known as the lithium problem. It does not overturn the Big Bang model, but it does remind us that even well-established theories can have open questions, and that science continues to refine its understanding over time. Still, the overall agreement between predicted and observed abundances remains striking. It is not just a coincidence, it is a confirmation. Because if the universe had not passed through a hot, dense phase, there would be no reason for these specific proportions to exist. They are a signature, a kind of chemical fingerprint, left behind by the earliest processes in cosmic history. So when we look at the composition of the universe today, when we observe hydrogen clouds, when we measure helium in distant galaxies, we are seeing the outcome of events that took place within the first few minutes. Moments when the universe was still young, still simple, but already shaping the future. And in that quiet formation of the first nuclei, we find another piece of the larger story. Not just that the universe expanded, but that it evolved in ways that can be predicted, tested, and understood. A story written not only in light, but in the very matter that surrounds us as we trace the universe backward through expanding galaxies, through the glow of the cosmic microwave background, through the formation of the first atomic nuclei. We arrive at a point where our understanding becomes both remarkably precise and suddenly uncertain. Up to a certain moment, the story is clear. We can describe how the universe cooled, how particles formed, how light began to travel freely. But as we move closer to the very beginning, the conditions become so extreme that the familiar rules of physics begin to lose their clarity. And yet, even here, there is structure. There are stages, known as epochs, that describe how the universe evolved in its earliest moments. These are not directly observed, but they are inferred from well-tested physical theories, extended into conditions far beyond anything we can recreate on Earth. One of the earlier stages that can be meaningfully described is known as the quark epoch. This occurs within the first tiny fraction of a second, when the universe is still incredibly hot, with temperatures reaching trillions of degrees. At this stage, quarks and gluons, the fundamental components of protons and neutrons, exist in a kind of dense, energetic fluid. They're not yet bound into stable particles. Instead, they move freely, interacting constantly. As the universe expands and cools further, these quarks begin to combine, forming protons and neutrons in a process known as hadronization. This marks a transition from a more chaotic, high-energy state to one where recognizable particles begin to emerge. Soon after, within the first few seconds, the universe enters the lepton epoch, where particles such as electrons and neutrinos dominate the interactions. These stages, while brief, set the conditions for everything that follows. They determine how matter behaves, how energy is distributed, and how the universe evolves as it continues to expand. But even these early epochs, as extreme as they are, still fall within the reach of known physics. They can be described using a combination of quantum field theory and general relativity, at least to a certain extent. The real challenge appears when we try to go even further back, closer to what we might call the true beginning. At this point, we encounter what is known as the Planck epoch, and this is the earliest period for which we can attempt to define physical conditions, and it occurs at a time known as the Planck time, approximately 10 to the power of minus 43 seconds after the start of expansion. This number is almost impossible to visualize. If you were to divide a single second into smaller and smaller intervals, down to unimaginably tiny fractions, the Planck time would still be far beyond what intuition can grasp. It represents a boundary, not just in time, but in knowledge. At the Planck epoch, temperatures are thought to reach about 10 to the power of 32 degrees Kelvin. Energy densities become so high that gravity itself must behave according to quantum principles, and this is where the difficulty arises. We have two incredibly successful theories: general relativity, which describes gravity, and the large-scale structure of space-time, and quantum mechanics, which describes the behavior of particles at the smallest scales. Both have been tested extensively, and both work extraordinarily well within their domains. But they are not fully compatible. General relativity treats space-time as a smooth, continuous fabric. Quantum mechanics introduces uncertainty, fluctuations, and discrete interactions. When we try to apply both theories at once, under the extreme conditions of the early universe, inconsistencies appear. The equations no longer provide reliable answers. Predictions become unstable or undefined. This is why physicists believe that a deeper theory is needed, a theory of quantum gravity, and such a theory would unify general relativity and quantum mechanics, describing how gravity behaves at the smallest scales and how space-time itself might be structured at those levels. Several approaches have been proposed. String theory, developed by researchers including Leonard Susskind and others, suggests that fundamental particles are not point-like, but rather tiny vibrating strings existing in higher dimensional spaces. Loop quantum gravity, advanced by scientists such as Carlo Rovelli and Abhay Ashtekar, proposes that space-time itself has a discrete structure, composed of tiny quantized units. Both approaches offer insights, but neither has yet been confirmed as a complete description of reality. And so, when we reach the Planck epoch, we arrive at a boundary, not necessarily the beginning itself, but the limit of what current physics can describe with confidence. Beyond this point, the question of what happened becomes more uncertain. It is important to understand what this uncertainty means. It does not mean that nothing existed. It does not mean that the universe suddenly appears without cause or structure. It simply means that our current tools, our equations, our theories, are not yet sufficient to describe those conditions fully. Science is very good at identifying what it knows, and equally important, what it does not yet know, and in this case, the unknown lies at the very earliest moment, or perhaps at the very concept of a moment itself. Because as we approach these extremes, even the idea of time becomes less clear. The quantum fluctuations, temporary changes in energy that occur even in empty space, may have played a role. Space-time itself may not have been smooth, but instead subject to constant, rapid variations. Some physicists describe this as a kind of quantum foam, a state where the geometry of space-time is constantly shifting at incredibly small scales. In such a scenario, the distinction between past and future may not be well defined. Causality, the idea that one event leads to another, may behave differently, or may not apply in the way we expect. This brings us back to the original question, but with a new perspective. What does it mean to ask what started the universe, if time itself may not be well defined at the earlier stages, or if time emerges along with the expansion of the universe, then the idea of a before may not apply in a straightforward way. It is not that there is a hidden answer waiting to be discovered, like a missing piece of a puzzle. It may be that the question itself needs to be rethought. And yet, this does not make the exploration any less meaningful. In fact, it highlights the depth of what we are trying to understand. Because even though we cannot yet describe the very beginning with certainty, we can describe what came immediately after with remarkable detail. We can trace the evolution of the universe from fractions of a second onward. We can test our models against observation. We can refine our theories, and push the boundaries of knowledge further. And in doing so, we gradually illuminate the path, even if the starting point remains just beyond reach. So as we approach the earliest moments, we find ourselves in a place where science is both powerful and humble. Powerful in its ability to reconstruct vast stretches of cosmic history, humble in its recognition that some questions remain open, and perhaps that balance is part of what makes this exploration so compelling. Because the closer we get to the beginning, the more we're reminded that understanding the universe is not just about finding answers, but about learning how to ask the right questions. As the picture of the early universe began to take shape, one idea kept returning, quietly persistent and slightly puzzling. The universe looks remarkably uniform. No matter where we look, in one direction or another, across billions of light years, the large-scale properties of the universe are almost the same. The cosmic microwave background, for example, shows nearly identical temperatures in every direction, differing by only a few parts in 100,000. At first glance, this might seem expected, but when scientists examined it more closely, it raised a surprising question. How did distant regions of the universe become so similar, if they were never in contact? To understand this, it helps to consider how information travels. Nothing can move faster than the speed of light. So if two regions of space are separated by a great distance, there must have been enough time for light, or any signal, to travel between them in order for them to exchange energy, to reach the same temperature, to become uniform. But when cosmologists calculated the distances involved and compared them to the age of the universe, something did not quite add up. There simply had not been enough time. This is known as the horizon problem. It suggests that distant regions of the universe, which appear almost identical, should not have been able to influence each other, and yet they clearly share the same properties. There was another issue as well. When scientists studied the overall geometry of the universe, they found that it appears to be very close to flat. Not flat in the everyday sense, but in a geometric sense, meaning that the rules of Euclidean geometry apply on large scales. Parallel lines remain parallel. The angles of a triangle add up to 180 degrees. This might sound like a small detail, but it has deep implications, because in general relativity, the geometry of the universe depends on its total energy density. If the density is too high, the universe would be curved like a sphere. If it is too low, it would be curved like a saddle. For the universe to be nearly flat, the density must be very close to a specific value, often called the critical density, and not just close, but extremely close. Early calculations showed that even a tiny deviation from this value in the early universe would have led to a dramatically different geometry today. This is known as the flatness problem. So now there were two puzzles. Why is the universe so uniform across vast distances, and why is its geometry so finely balanced? In the early 1980s, a physicist named Alan Guth proposed a solution that was both simple in concept and profound in its implications. He suggested that the universe underwent a brief period of extremely rapid expansion, very early in its history. This idea became known as cosmic inflation. According to inflation theory, the universe did not expand at a steady rate from the very beginning. Instead, for a tiny fraction of a second, it expanded exponentially. This means that its size increased by an enormous factor in an incredibly short time. To give a sense of scale, Imagine taking something smaller than a proton and expanding it to a size larger than the observable universe in less than a trillionth of a second. It sounds almost impossible, but within the framework of quantum field theory and general relativity, it is a mathematically consistent idea. The key mechanism behind inflation involves a type of energy associated with the field, often called the inflaton field. In simple terms, this field has a high energy density that remains nearly constant for a brief period, and when energy density behaves in this way, it can drive rapid expansion. In fact, the equations of general relativity show that a constant energy density can cause space to expand at an accelerating rate. In words, this relationship can be described as a nearly constant energy density leads to exponential growth of the scale of the universe over time. During inflation, space itself stretches dramatically, and this stretching has important consequences. First, it solves the horizon problem. Before inflation, the universe was much smaller. Regions that are now far apart were once close enough to interact, to exchange energy, to reach the same temperature. Then inflation stretched those regions apart, preserving their uniformity across vast distances. Second, it addresses the flatness problem. Rapid expansion smooths out any initial curvature, much like inflating a balloon makes its surface appear flatter over larger areas. As space expands exponentially, the geometry approaches flatness, regardless of its initial shape. So inflation provides a natural explanation for why the universe appears so uniform and so close to flat. But the idea goes even further. During inflation, tiny quantum fluctuations, minute variations in energy at the smallest scales, are stretched along with space. These fluctuations become larger and are effectively frozen into the structure of the universe. Later, as the universe continues to evolve, these small variations grow under the influence of gravity. They become the seeds of galaxies, clusters, and large-scale structures. This connection between quantum fluctuations and cosmic structure is one of the most remarkable aspects of inflation. It suggests that the patterns we observe in the distribution of galaxies and in the cosmic microwave background originated from processes occurring at incredibly small scales in the earliest moments of the universe. Alan Gough's original model was later refined and expanded by other physicists, including Andre Linde. Linde developed what is known as chaotic inflation, a version of the theory that allows inflation to occur under a wider range of conditions. He also explored the idea of eternal inflation, where inflation continues in different regions of space, potentially giving rise to multiple universes. These developments pushed inflation from a single event into a broader framework with far-reaching implications. But even in its simplest form, inflation makes testable predictions. It predicts a specific pattern of fluctuations in the cosmic microwave background. It predicts a nearly scale invariant distribution of these fluctuations, meaning that variations occur in a similar way across different sizes. Observations from missions such as WME, P and Planck have confirmed these predictions with remarkable precision. The data shows exactly the kind of subtle variations that inflation predicts. This does not mean that every detail of inflation is fully understood. There are still open questions about the exact nature of the inflaton field and how inflation began and ended, but the overall framework fits the evidence extremely well, and perhaps most importantly, It connects several seemingly unrelated observations into a single, coherent picture. A universe that is expanding. A universe that is uniform on large scales. A universe that contains small variations, which later grow into structure. All of these features can be understood if there was a brief period, when space itself expanded at an extraordinary rate. So in addition to the steady expansion that continues today, the universe may have experienced a sudden, dramatic growth, very early in its history, a moment when space stretched so rapidly that it reshaped the entire structure of the cosmos, and in that rapid expansion, we find a possible answer to why the universe looks the way it does today. In the earlier stages of the universe, everything was almost perfectly smooth. Matter was spread out with remarkable uniformity. Light filled all of space, and on the larger scales there were no stars, no galaxies, no clusters, just a vast, expanding sea of energy and particles, and yet, within that near uniformity, there were tiny imperfections, subtle variations, so small that they amounted to differences of only a few parts in 100,000. Almost nothing, but not quite nothing. These small irregularities are known as density fluctuations. They represent regions where matter was slightly more concentrated and regions where it was slightly less so, and those tiny differences, almost imperceptible at the time, would eventually grow into everything we see today. The origin of these fluctuations is believed to lie in quantum mechanics. At the smallest scales, energy is never perfectly uniform, even in what we might call empty space. There are constant, unavoidable variations. These are known as quantum fluctuations. They arise from the uncertainty principle, a fundamental concept in quantum mechanics that states, in words, that the more precisely we know the position of a particle, the less precisely we can know its momentum, and vice versa. This uncertainty is not due to measurement limitations. It is built into the fabric of reality. During the period of cosmic inflation, these tiny quantum fluctuations were stretched dramatically. What began as microscopic variations, smaller than an atomic nucleus, were expanded to cosmic scales. They became embedded in the distribution of matter and energy across the universe. At first, these fluctuations were still extremely small, but gravity has a simple and powerful effect. It amplifies differences. Regions that are slightly denser exert a slightly stronger gravitational pull. They attract more matter. As more matter gathers, the region becomes even denser, increasing its gravitational influence further. This process is known as gravitational collapse. It is not a sudden event, but a gradual one. Over millions and billions of years, matter slowly accumulates in these denser regions. Clouds of gas begin to form. Within those clouds, pressure and gravity interact, leading to the formation of the first stars. Stars group together into galaxies. Galaxies gather into clusters, and clusters connect into vast networks. What begins as a nearly uniform distribution evolves into a complex structure, sometimes described as the cosmic web. This web is not random. It has a distinct pattern, with filaments of matter stretching across enormous distances, intersecting at dense nodes where galaxy clusters reside, and vast voids where very little matter is found. The scale of these structures is difficult to fully grasp. Filaments can span hundreds of millions of light years. Voids can be equally vast. And yet, All of this complexity traces back to those tiny fluctuations in the early universe. There is another important ingredient in this process, something that does not emit light, does not interact with radiation in the usual way, and yet plays a central role in structure formation. This is known as dark matter. Dark matter does not absorb, emit, or reflect light. It cannot be seen directly, but its presence can be inferred through its gravitational effects. Galaxies rotate faster than they should if only visible matter were present. Clusters of galaxies hold together more strongly than expected. Light passing near massive objects is bent, revealing more mass than can be accounted for by stars and gas alone. All of these observations point to the existence of dark matter, and in the early universe, dark matter played a crucial role. Unlike ordinary matter, which interacts with radiation and was initially coupled to it, dark matter does not interact with light. This allowed it to begin clumping earlier, forming gravitational wells. As the universe cooled and ordinary matter decoupled from radiation, it began to fall into these wells, enhancing the process of structure formation. In this way, dark matter acts as a kind of invisible scaffolding. It shapes the large-scale structure of the universe, guiding the formation of galaxies and clusters. Without it, the universe would likely look very different. Structures would form more slowly, and the patterns we observe today might not exist at all. To study these structures, astronomers conduct large surveys of the sky. One of the most significant is the Sloan Digital Sky Survey, a long-term project that has mapped the positions of millions of galaxies. By analyzing this data, scientists can reconstruct the large-scale distribution of matter. They can see the cosmic web, not as an abstract concept, but as a measurable structure. These observations match the predictions made by cosmological models, including those based on inflation and the growth of fluctuations. The agreement is striking. These simulations that begin with tiny fluctuations, based on measurements from the cosmic microwave background, evolve into structures that closely resemble what we actually observe. This consistency provides strong support for the overall framework. It shows that the same principles, applied across vast spans of time, can explain both the early simplicity and the later complexity of the universe. There is something quietly remarkable about this progression. The universe begins in a state that is almost uniform, almost featureless, and from that simplicity, through the combined effects of quantum fluctuations, gravitational attraction, and cosmic expansion, it develops into a rich and varied structure. Stars ignite, galaxies form, planets emerge, and eventually, conditions arise where life becomes possible. All of this, from fluctuations so small that they were once nearly indistinguishable from perfect uniformity. It is a reminder that complexity does not always require dramatic beginnings. Sometimes, it grows from the smallest of differences, given enough time and the right conditions. And in this case, those conditions were set in the earliest moments of the universe, moments when tiny variations were stretched across cosmic scales, quietly shaping everything that would follow. From the largest galaxy clusters to the stars in the night sky, to the atoms that make up everything around you, all tracing back to fluctuations, barely there at all. By this point, a clear picture has begun to emerge. The universe is expanding. It was once hotter, denser, more uniform. It contains a faint background radiation, and a specific mixture of light elements, all pointing toward a common early state, taken together. These observations form what we call the Big Bang model, and it is important to be precise about what that model actually describes. The Big Bang theory explains how the universe has evolved from an early hot, dense phase into the vast, structured cosmos we observe today. It describes expansion. It describes cooling. It describes the formation of particles, nuclei, atoms, stars, and galaxies. But it does not fully explain what started the universe in the first place. That distinction is subtle, but essential. Because when people hear the phrase Big Bang, it is often taken to mean the absolute beginning of everything. A moment when the universe came into existence from nothing, fully formed in its laws and properties. In reality, the Big Bang model does not make that claim. Instead, it describes the evolution of the universe from a very early state onward. It tells us what happened after expansion began, not necessarily why it began. This leaves room for important questions. What determined the initial conditions of the universe? Why did it begin in such a hot, dense state? Why are the laws of physics what they are, and not something different? These are not small questions. They sit at the boundary between cosmology, the study of the universe as a whole, and fundamental physics, which seeks to understand the underlying laws that govern everything. Cosmology uses observations and established theories, such as general relativity and quantum field theory, to describe how the universe evolves. Fundamental physics asks deeper questions about the origin of those laws themselves, and while the two fields overlap, they are not identical. There is a region where our current understanding becomes less certain, a kind of conceptual boundary, where tested theory transitions into open questions. Within this boundary, some aspects of the Big Bang model are extremely well supported. The expansion of the universe, confirmed through observations of galactic redshift, the cosmic microwave background, measured in detail by missions such as COBE, WMAP, and Planck, the abundance of light elements, matching predictions from Big Bang nucleosynthesis. These are not speculative ideas. They are grounded in observation, tested repeatedly, and widely accepted within the scientific community. But as we move closer to the earliest moments, the situation changes. The conditions become more extreme. Energy densities increase. Quantum effects become more significant. And our current theories, while powerful, begin to lose their reliability. This is where open questions emerge. For example, what caused the initial expansion? Was it triggered by a specific physical process? Or is it a natural consequence of deeper laws? Did the universe begin from a singularity, a point where density becomes infinite? Or does that concept simply reflect a limitation in our equations? And what about time itself? If time began with the expansion of the universe, then asking what came before may not be meaningful in the usual sense. But if time has a more complex structure, perhaps emerging from deeper principles, then the question may need to be reframed rather than dismissed. There are also questions about the uniformity of the universe. Inflation provides a compelling explanation, but it introduces its own uncertainties. What is the nature of the inflaton field? How did inflation start, and how did it end? Are there multiple inflationary regions, or even multiple universes? These are areas of active research, where ideas are still being developed and tested. It is important to recognize that uncertainty is not a weakness in science. It is a natural and necessary part of the process. Science does not claim to have all the answers. Instead, it builds a framework of understanding, supported by evidence, and continually refined as new data becomes available. In this sense, the Big Bang model is both robust and incomplete. Robust in its ability to explain a wide range of observations with remarkable consistency. Incomplete in that it does not yet provide a full account of the universe's ultimate origin. This balance is what makes cosmology such an interesting field. It combines well-established knowledge with deep, unresolved questions. It allows us to speak with confidence about certain aspects of the universe while remaining open to new ideas about others, and it encourages a kind of careful curiosity, not rushing to conclusions, not filling gaps with assumptions, but gradually extending understanding through observation and theory. There is also something quietly reassuring in this approach, because it means that the story of the universe is not fixed. It is still being explored, still being refined, still unfolding. And as we move forward, the questions become more speculative, but also more intriguing. If the Big Bang does not fully explain the origin, then what might lie beyond it? Are there deeper mechanisms, hidden within quantum physics, or within the structure of space-time itself? Could the universe have emerged from a different kind of state? One that does not fit neatly into our current categories. These are the kinds of ideas that begin to appear at the edges of our understanding. They are not yet confirmed, they are not yet fully developed, but they represent the next steps in the exploration. So while the Big Bang provides a powerful and well-supported description of the universe's evolution, it also opens the door to further questions. Questions that reach beyond expansion, beyond early conditions, and toward the deeper foundations of reality itself. And it is within that space, between what we know and what we're still trying to understand, that the search for the true beginning continues. When people hear the word nothing, it often brings to mind a kind of absolute emptiness, a complete absence of everything. No matter, no energy, no space, no time, just nothing at all. But in physics, the meaning of nothing is far more subtle, and in some ways, far more interesting. Because what physicists call a vacuum, what might casually be described as empty space, is not truly empty. It is filled with fields. Invisible, but fundamental. These fields exist everywhere, and even in their lowest energy state, they're not perfectly still. They fluctuate, constantly and unavoidably. This behavior is a direct consequence of quantum mechanics. At the smallest scales, the universe does not allow perfect stillness. The uncertainty principle, first formulated by Werner Heisenberg in the 1920s, states, in words, that it is impossible to know both the exact energy and the exact timing of a system with complete precision. And from this principle, something surprising follows. Energy can briefly appear and then disappear, as long as it does so within a very short time. These temporary changes are known as quantum fluctuations. They are not just theoretical. They have measurable effects, such as the Casimir effect, where two closely spaced metal plates experience a small force due to fluctuations in the vacuum between them. So even in what we might call empty space, there is activity, there is structure, there is energy fluctuating at the smallest scales. This leads to an intriguing possibility. What if the universe itself emerged from such a fluctuation? In the 1970s, physicist Edward Tryon proposed an idea that was both simple and bold. He suggested that the universe could be a large-scale quantum fluctuation arising from the vacuum. In his words, the universe might be a free lunch. The phrase was not meant casually. It reflected a specific idea about energy. If the total energy of the universe is zero, then its existence might not violate conservation laws. That positive energy, in the form of matter and radiation, could be balanced by negative gravitational energy. In simplified terms, gravity can be thought of as contributing negative energy because it binds systems together. So if the total energy adds up to zero, the universe could, in principle, arise without requiring an external input of energy. This is not a complete explanation, but it shows how quantum ideas can change the way we think about origins. Another approach was developed by Alexander Vilenkin, who explored what is known as the tunneling from nothing model. In quantum mechanics, particles can sometimes pass through barriers that would be impossible to cross according to classical physics. This process is called quantum tunneling. It does not involve breaking the rules, but rather reflects the probabilistic nature of quantum systems. Vilenkin applied this idea to the universe as a whole. He proposed that the universe could have tunneled into existence, transitioning from a state with no classical space-time into an expanding universe. Again, the word nothing here does not mean absolute absence. It refers to a state without classical space and time, but still governed by quantum laws. In this framework, the universe does not emerge from a pre-existing space. Instead, space-time itself appears as part of the process. This challenges the way we usually think about beginnings, because in everyday experience, events happen within space and time, but here, space and time are part of what is being created. It is a bit like asking where a story takes place before the story itself has been written. The question assumes a context that does not yet exist. These ideas remain theoretical, and they are not yet confirmed by direct observation. But they are grounded in established principles of quantum mechanics. They attempt to extend those principles to the largest possible scale, the universe itself. There is also the concept of vacuum energy, which plays a central role in these discussions. In quantum field theory, each field has a lowest possible energy state, known as the vacuum state. But even this lowest state is not zero. There's always some residual energy, due to fluctuations. This vacuum energy is thought to be related to dark energy, the mysterious component driving the accelerated expansion of the universe today. Although the exact connection is still not fully understood, it highlights the idea that even empty space contains energy and can influence the dynamics of the universe. So when physicists speak of a universe emerging from nothing, they are not referring to a simple void. They are referring to a state that is described by quantum laws, where fluctuations can occur and where space-time itself may not yet be defined in the usual way. This is a very different kind of nothing than what we might imagine intuitively. It is structured, governed by principles, and capable of giving rise to complex behavior. Of course, this raises further questions. Why do these quantum laws exist? Why does the vacuum have the properties it does? Why is there something rather than nothing in the most fundamental sense? These questions move beyond physics into deeper philosophical territory, but within the framework of modern science, models like those proposed by Tryon and Vilenkin offer a way to think about cosmic origins without requiring a classical cause. They suggest that the universe could emerge naturally as a consequence of quantum behavior, not from a pre-existing explosion, not from a specific location, but from the inherent properties of reality at its most fundamental level. It is worth noting that these ideas are still being explored. They are part of an active area of research, where cosmology and quantum theory intersect. New models are developed, refined, and tested against observation wherever possible. And while definitive answers remain elusive, the direction of inquiry is clear. To understand the beginning of the universe, we may need to understand the nature of nothing itself, not as an absence, but as a dynamic, fluctuating state, rich with possibility. And in that quiet activity, in those smallest of fluctuations, there may lie the seeds of everything that followed. There is a quiet assumption that often goes unnoticed. That space is something fundamental. That time is something that simply exists. That the universe is built out of matter, moving through a pre-existing stage. But over the past several decades, some physicists have begun to explore a different possibility. What if space and time are not fundamental at all? What if they emerge from something deeper, something more abstract, and perhaps more subtle? One of the earliest voices to suggest this kind of idea was John Archibald Wheeler. And Wheeler was a theoretical physicist who worked on general relativity, quantum mechanics, and the nature of information, and he proposed a phrase that has since become well known: it from bit. It sounds almost playful, but it carries a profound meaning. In Wheeler's view, every physical quantity, every particle, every field, every aspect of reality ultimately arises from information, from binary choices, yes or no, 1 or 0. In other words, the universe may not be built from matter first, but from information. And what we perceive as physical reality may be a manifestation of that underlying informational structure. This idea connects physics to a field known as information theory, originally developed by Claude Shannon in the mid-20th century. Information theory studies how information is stored, transmitted, and processed. And it turns out that many physical systems can be described in terms of information. Entropy, for example, is not just a measure of disorder, it is also a measure of information. In thermodynamics, entropy describes how energy is distributed. In information theory, it describes uncertainty, or the number of possible states a system can have. These two meanings are deeply connected, and this connection becomes especially important in modern physics, because if information is fundamental, then the structure of the universe may be shaped by how information is organized and transformed. This idea has led to new ways of thinking about space and time. One approach is known as emergent space-time. Instead of treating space-time as a basic ingredient, this perspective suggests that it arises from more fundamental relationships, much like temperature emerges from the motion of particles, even though temperature itself is not a particle. A specific example of this idea appears in the work of Eric Verlinde. Verlinde proposed a model known as emergent gravity, where gravity is not a fundamental force, but an emergent phenomenon. In this view, gravity arises from changes in information associated with the positions of matter. It is related to entropy and to how information is distributed across space. In simplified terms, objects move in response to gradients in information, much like systems evolve toward states of higher entropy. This is a very different way of thinking about gravity. Instead of being a force that pulls objects together, it becomes a consequence of deeper statistical behavior. And while this idea is still being explored and debated, it reflects a broader trend in theoretical physics, a shift toward understanding reality in terms of information and relationships, rather than just particles and forces. Another perspective comes from Seth Lloyd, a physicist at the Massachusetts Institute of Technology. Lloyd has described the universe as a kind of quantum computer, not a machine built with circuits and processors, but a system that processes information through physical interactions. In this view, every interaction between particles, every exchange of energy, every change in state can be thought of as a computation. The universe evolves by processing information, step by step, according to the laws of physics. This does not mean that the universe is literally a computer in the everyday sense, but it suggests that computation, the transformation of information, is a fundamental aspect of how reality operates. And when we combine these ideas, a new picture begins to form, a picture in which space, time, matter, and energy are not the deepest layer of reality. Instead, they emerge from something more abstract, from patterns of information, from relationships, from the ways in which systems can exist and evolve. There are also connections to quantum entanglement, one of the most intriguing features of quantum mechanics. When two particles become entangled, their states are linked, even when they are separated by large distances, which changes in one particle are correlated with changes in the other, in a way that cannot be explained by classical communication. Some researchers have proposed that space-time itself may be built from networks of entangled particles, that the geometry of space, the distances between points, may arise from the strength and structure of these connections. In this sense, space is not a fixed background. It is a result of relationships, a kind of network, woven from information. If this is true, then the beginning of the universe may not be a moment when space suddenly appeared. It may be a transition from a state where these relationships were not yet organized, into one where space-time emerges as a coherent structure. This is still a developing area of research. The mathematics is complex, and the ideas are not yet fully tested. But they offer a different way of thinking about origins, not as a single event, but as an emergence, a gradual unfolding, where the familiar concepts of space and time arise from deeper principles. There is something quietly elegant about this perspective. It suggests that the universe does not require a predefined stage, that the stage itself, space and time, is part of the performance, and that the underlying script, if there is one, may be written in the language of information. Of course, this raises new questions. If information is fundamental, where does it come from? What determines its structure? Why do the laws of physics take the form they do? These questions remain open, but they point toward a deeper level of understanding, one that goes beyond particles, beyond forces, and into the foundations of reality itself. So as we consider the origin of the universe, we're not limited to thinking in terms of matter and energy alone. We can also ask how information behaves, how it is stored, how it changes, and how it gives rise to the structures we observe. And in doing so, we begin to see the universe in a different light, not just as a collection of objects, but as a dynamic system of information, unfolding, evolving, and giving rise to space, to time, and to everything within them. there is a simple idea that feels almost impossible at first, that everything you experience in 3 dimensions, length, width, and depth, might be described completely by information stored on a 2-dimensional surface. It sounds like something from science fiction. But in modern physics, this idea is taken seriously. It is known as the holographic principle, and it begins with a question about information. In the 1970s, physicist Jacob Bekenstein studied black holes and made a surprising observation. He found that the amount of information, or entropy, contained within a black hole is not proportional to its volume. Instead, it is proportional to the area of its surface. More specifically, the entropy is proportional to the surface area of the event horizon, the boundary beyond which nothing can escape. This result was later refined by Stephen Hawking, leading to what is known as the Bekenstein-Hawking entropy formula. In words, it can be described as the entropy of a black hole is proportional to the area of its event horizon, not its volume. This is unusual. In most physical systems, the amount of information or entropy scales with volume, a larger space, more room for particles, more possible configurations. But black holes seem to follow a different rule. All the information about what falls into them, everything that contributes to their entropy, appears to be encoded on their surface. This led Gerard 't Hooft and Leonard Susskind to propose a bold generalization. What if this is not just a property of black holes, but a fundamental feature of the universe? What if all the information contained within a region of space can be described by information stored on its boundary? This is the holographic principle. The name comes from holograms, 2-dimensional surfaces that can encode 3-dimensional images. If you've ever seen a holographic image, you may notice that even though it is stored on a flat surface, it appears to have depth. It contains information that allows the reconstruction of a 3-dimensional structure. In a similar way, the holographic principle suggests that the 3-dimensional universe we experience may be a projection or an emergent description of information encoded on a lower dimensional boundary. To explore this idea further, physicists developed more precise mathematical models. One of the most important is known as the ADS-CFT correspondence, proposed by Juan Maldacena in the late 1990s. The name stands for anti-de Sitter space and conformal field theory. It describes a relationship between 2 very different types of physical theories. On one side, there is a theory of gravity defined in a higher dimensional space. On the other, there is a quantum field theory without gravity, defined on the boundary of that space. And remarkably, these 2 descriptions are mathematically equivalent. They describe the same physics in different ways. This is not just an analogy, it is a precise correspondence. Calculations performed in one framework can be translated into the other. This provides strong support for the idea that information on a boundary can fully describe what happens in a higher dimensional space. Now, the specific geometry used in ADS-CFT does not exactly match our observable universe, but the principle itself that such dual descriptions can exist has far-reaching implications. It suggests that the dimensionality of space, the fact that we experience 3 dimensions, may not be fundamental. Instead, it may emerge from a deeper structure, encoded in fewer dimensions. This raises an interesting possibility. When we think about the beginning of the universe, we often imagine a 3-dimensional space expanding from a dense state. But if the holographic principle applies, then the true description of that early universe might not be three-dimensional at all. It might be encoded on a boundary, in a form that does not directly resemble the space we experience. In this view, the expansion of the universe could correspond to changes in how information is organized, rather than simply the stretching of space. Space-time itself, with its geometry and dimensions, may arise from more fundamental relationships. There are also connections between the holographic principle and quantum entanglement. Some researchers have proposed that the structure of space-time is linked to patterns of entanglement between quantum systems. In this framework, the geometry of space emerges from the way information is shared and correlated. Stronger connections correspond to closer distances. Weaker connections correspond to greater separation. So space, in this sense, becomes a map of relationships, a network, defined not by physical distance alone, but by the structure of information. This idea is still being explored, and it is not yet fully understood. But it offers a new way of thinking about reality, not as a fixed stage with objects placed within it, but as something that emerges from deeper principles where information, boundaries, and relationships play a central role. There is also something quietly elegant about the holographic principle. It suggests that the universe may be more efficient than it appears, that the vast complexity of three-dimensional space, with its enormous volumes, can be described using information that scales with area, not volume, a kind of compression built into the fabric of reality. Of course, this does not mean that what we experience is an illusion. The three-dimensional world is real, in the sense that it is consistent, measurable, and governed by physical laws. But it may not be the most fundamental description. It may be a higher-level representation, emerging from something simpler and more abstract. So when we consider the origin of the universe, we can begin to ask new kinds of questions, not just how space expanded, but how the information that defines space was organized. Not just what happened in 3 dimensions, but what underlying structure made those dimensions possible. And in that shift, from volume to boundary, from objects to information, we find another perspective on the beginning, one where the universe, in all its depth and complexity, may be written on a surface, quietly encoding everything that unfolds within it. There is a quiet assumption that sits beneath many descriptions of the universe, that everything began once, at a single moment, and has been unfolding ever since. A beginning, followed by expansion, followed by the gradual development of structure. It is a simple picture, and in many ways, it works very well. But some physicists have explored a different possibility. What if the universe did not begin just once? What if it has gone through multiple phases, cycles, or transitions, extending far beyond what we usually imagine? These ideas fall under a broad category of models that include cyclic universes, bouncing cosmologies, and other alternatives to a singular beginning. They do not reject the evidence for expansion or the early hot, dense state. Instead, they reinterpret what that state represents. Not necessarily the absolute beginning, but perhaps a transition from something that came before. One of the most well-known proposals in this area comes from Roger Penrose, a mathematician and physicist known for his work on general relativity and black holes. Penrose introduced a model called conformal cyclic cosmology, often abbreviated as CCC. In this model, the universe does not have a single beginning and end. Instead, it consists of a sequence of cycles, which Penrose calls aeons. Each aeon begins with a Big Bang-like expansion and ends in a state where the universe has expanded so much and cooled so completely that its structure becomes extremely simple. In this far future state, galaxies have moved apart, stars have burned out, and most matter has decayed or been absorbed into black holes. Eventually, even black holes evaporate through a process known as Hawking radiation. At this point, the universe is dominated by radiation, with very little structure remaining. Penrose argues that in this state, the concept of scale loses its meaning. Without massive objects, there are no natural rulers, no preferred distances. In this limit, the geometry of space-time can be transformed in such a way that the end of one aeon becomes mathematically equivalent to the beginning of the next. So instead of a singular starting point, the universe transitions smoothly from one cycle to another. Each new expansion emerges from the distant future of the previous one. This idea is elegant, but also speculative. It makes certain predictions, such as subtle patterns in the cosmic microwave background, that could reflect events from a previous aeon. Some researchers have claimed to find hints of such patterns, while others remain unconvinced. As with many ideas at the edge of cosmology, the evidence is still being debated. Another approach to avoiding a singular beginning comes from loop quantum cosmology, a field developed from loop quantum gravity. This framework is associated with researchers such as Carlo Rovelli and Abhay Ashtekar. In loop quantum gravity, space-time is not continuous. Instead, it is made up of discrete units, often described as tiny loops or networks. At very small scales, space has a kind of granular structure. When these ideas are applied to cosmology, they lead to a striking result. The equations suggest that as the universe contracts, approaching what would traditionally be considered a singularity, quantum effects become dominant. For instead of density increasing without bound, a repulsive effect emerges, caused by the quantum properties of space-time. This prevents the formation of a singularity, and instead of a collapse into an infinitely dense point, the universe undergoes a bounce, a transition from contraction to expansion. This is known as the Big Bounce. In this model, the expanding universe we observe today could have been preceded by a contracting phase, a previous universe shrinking over time, eventually reaching extremely high density and then reversing into expansion. This idea preserves many features of the Big Bang model, such as the hot, dense early state, while replacing the singular beginning with a transition. It also raises interesting questions about what conditions might have existed before the bounce. Was the previous universe similar to ours? Did it have galaxies, stars, and structure? Or was it fundamentally different? These questions are still open, and the models are still being developed. There are also hybrid models, combining aspects of cyclic behavior and quantum effects. Some theories suggest that the universe may undergo repeated cycles of expansion and contraction, driven by different physical mechanisms. Others explore the possibility that multiple regions of space evolve independently, each experiencing its own sequence of events. Despite their differences, these models share a common feature. They challenge the idea of a single, absolute beginning. They suggest that what we perceive as the start of the universe may be part of a larger, ongoing process. Of course, any such model must be consistent with observation. It must account for the expansion of the universe, the cosmic microwave background, the abundance of elements, and the large-scale structure we observe. This is where observational constraints become important. The cosmic microwave background, in particular, provides a detailed snapshot of the early universe. Any alternative model must reproduce its features, including its near uniformity and the pattern of fluctuations. Similarly, measurements of cosmic expansion and the distribution of galaxies place limits on how the universe could have evolved. So far, the standard Big Bang model, combined with inflation, remains the simplest explanation that fits all available data, but alternative models continue to be explored, refined, and tested. They offer new perspectives, and sometimes highlight aspects of the standard model that require deeper understanding. There is also a broader philosophical dimension to these ideas. If the universe is cyclic, or if it undergoes repeated bounces, then the concept of a beginning becomes less clear. Instead of a single starting point, there may be an ongoing sequence without a clear origin. Time itself, in such models, may extend indefinitely in both directions, or it may be structured in cycles, with each phase connected to the next. This does not necessarily make the universe simpler. In some ways, it makes it more complex, but it also offers a different kind of explanation, one that replaces the question of what started everything with a question about processes, transitions, and patterns that repeat or evolve over time, and perhaps that shift from a single beginning to an ongoing process is part of what makes these ideas so intriguing. They suggest that the universe may not be defined by a single moment, but by a continuous unfolding, where expansion, contraction, and transformation are all part of a larger story, still being understood. As our understanding of the universe has deepened, another question has begun to take shape. Not just how the universe began, but why it has the particular properties that it does. Why are the laws of physics the way they are? Why do the fundamental constants have the values we measure? Why does gravity have its specific strength and not something slightly different? At first, these questions might seem abstract, but small changes in these values could have profound consequences. If the strength of gravity were even slightly different, stars might not form in the same way. If the balance between fundamental forces shifted, atoms might not be stable. If certain constants varied, the chemistry required for life might not be possible at all. And yet, in our universe, these values appear to fall within a narrow range that allows complex structures to exist. This observation has led some physicists to consider a broader possibility. What if our universe is not the only one? What if there are many universes, each with different properties, and we happen to exist in one where the conditions allow for observers? This idea is known as the multiverse. It is not a single theory, but a collection of related concepts that arise from different areas of physics. One of the most influential versions comes from inflationary cosmology. As we explored earlier, inflation describes a period of rapid expansion in the early universe. But in some models, particularly those developed by Andre Linde, inflation does not end everywhere at once. Instead, it continues in some regions, while stopping in others. This leads to a picture known as eternal inflation. In this framework, the universe is constantly generating new regions, often called bubble universes. Each bubble undergoes its own expansion, becoming a universe with its own properties. These regions are separated by rapidly expanding space, making them effectively unreachable from one another. So while they may exist, they do not interact directly. Each one evolves independently, with its own history. This idea naturally leads to variation. Different regions may settle into different physical states, depending on how the underlying fields behave. And this is where string theory enters the discussion. String theory is an attempt to unify all fundamental forces, including gravity, into a single framework. It proposes that the fundamental constituents of reality are not point-like particles, but tiny vibrating strings. The way these strings vibrate determines the properties of particles, such as their mass and charge. But string theory also introduces something unexpected. It allows for a vast number of possible solutions, often referred to as the string landscape. Each solution corresponds to a different way of configuring extra dimensions, which are predicted by the theory. These extra dimensions are not visible in everyday life because they are compactified, meaning they are curled up at extremely small scales. The specific way in which these dimensions are shaped influences the physical laws that emerge. Researchers such as Joseph Polchinski and Kamran Vafa have explored these ideas in detail, showing that the number of possible configurations may be extraordinarily large. Some estimates suggest numbers as high as 10 to the power of 500. This is not just a large number, it is almost beyond comprehension. Each configuration could correspond to a different universe, with different constants, different particle properties, and different physical laws. When combined with eternal inflation, the picture becomes even more expansive. Inflation creates new regions, and the string landscape provides a wide range of possible outcomes for those regions. Together, they suggest a multiverse in which many different types of universes exist. In such a scenario, the question of why our universe has its particular properties takes on a different form. Instead of asking why these constants were chosen, we might ask why we observe this particular set of constants. The answer could be related to what is known as the anthropic principle. In its simplest form, the anthropic principle states that we can only observe conditions that allow for our existence. If there are many universes with different properties, then it is not surprising that we find ourselves in one where stars, planets, and life are possible, or in universes where conditions are not suitable. There would be no observers to ask the question. This idea can feel both satisfying and unsettling. Satisfying, because it provides a possible explanation for why the universe appears finely tuned. Unsettling, because it suggests that some features of the universe may not have a deeper explanation, beyond the fact that they allow for observers. Of course, the multiverse remains a topic of active research and debate. One of the challenges is that other universes, if they exist, may be fundamentally unobservable. If they are separated by regions of space expanding faster than light can travel, then no signal from them could ever reach us. This raises questions about how such ideas can be tested and whether they fall within the domain of empirical science. Thus, some researchers have proposed indirect tests, looking for subtle signatures in the cosmic microwave background, or patterns that might indicate interactions between different regions. So far, no definitive evidence has been found, but the exploration continues. Even without direct confirmation, the multiverse framework has influenced how physicists think about fundamental questions. It provides a context in which variation is natural, rather than something that requires a unique explanation. It also highlights the possibility that the laws of physics, as we observe them, may not be universal in the deepest sense. They may be local, specific to our region of a much larger structure. And this brings us back to the original question, in a slightly different form. What started the universe? If there are many universes, perhaps the question becomes, what started the system that produces them? Is there a deeper mechanism underlying the multiverse itself, or is the multiverse the most fundamental level, beyond which there is no further explanation? These questions remain open, but they illustrate how our understanding has expanded from a single universe to the possibility of many, from fixed laws to a landscape of possibilities. And in that expanded view, our universe becomes one realization among many, with its own set of properties, quietly allowing the story of stars, galaxies, and life to unfold. There is a familiar idea from biology, one that describes how life evolves over time, variation, selection, and inheritance. Organisms vary in their traits. Some traits make survival and reproduction more likely, and over many generations, those traits become more common. It is a gradual process, unfolding over long periods, shaping the diversity of life we see today. Now imagine applying a similar idea, not to living organisms, but to entire universes. It sounds unusual, perhaps even a little unexpected, but this is precisely the direction explored by physicist Lee Smolin. Smolin proposed a concept known as cosmological natural selection. In this model, universes are not unique, isolated events. Instead, they may be part of a larger process where new universes are generated and their properties can vary. The mechanism at the center of this idea involves black holes. Black holes are among the most extreme objects in the universe. They form when massive stars collapse under their own gravity, compressing matter into a region of space-time where the gravitational pull becomes so strong that not even light can escape. At the core of a black hole, according to classical general relativity, lies a singularity, a point, or perhaps a region, where density becomes extremely high, and the curvature of space-time becomes extreme. But as we have seen before, singularities often signal a breakdown in our current theories, rather than a complete description of reality. So the question arises, what actually happens inside a black hole? One possibility, explored in Smolin's model, is that the collapse leading to a black hole could give rise to a new region of space-time. In other words, the interior of a black hole might not simply end in a singularity, as it might transition into a new expanding universe. If this is the case, then each black hole could be thought of as a kind of bridge, connecting one universe to another, a process of cosmic reproduction. And if each new universe has slightly different physical parameters, then over many generations, a form of selection could occur. Universes that produce more black holes would generate more offspring. Their properties would become more common in the overall population. This leads to an intriguing idea. The constants of physics, such as the strength of gravity, or the masses of fundamental particles, might be shaped by this process. The universes that are better at forming stars, and therefore black holes, would be more likely to reproduce. Over time, the population of universes could become dominated by those with properties that favor black hole formation. This does not imply intention or design. It is not a purposeful process. It is simply a consequence of variation and selection, applied at a cosmic scale, Of course, this idea depends on several assumptions. One of the most important is that black holes can indeed give rise to new universes, and this is not something we can currently observe directly. But there are hints, theoretical possibilities that make the idea worth exploring. For example, some solutions to Einstein's equations, such as those involving wormholes, suggest that space-time can connect different regions, or even different universes. In addition, models based on quantum gravity, including loop quantum gravity, have explored scenarios where singularity is replaced by bounces, similar to what we discussed earlier. In these models, the extreme conditions inside a black hole could lead to a transition, rather than an endpoint. There is also the black hole information paradox, a problem that has been studied extensively by physicists such as Stephen Hawking, Leonard Susskind, and many others. The paradox arises from a conflict between quantum mechanics and general relativity. Quantum mechanics suggests that information cannot be destroyed, but classical descriptions of black holes imply that information falling into them could be lost. Hawking showed that black holes emit radiation, now known as Hawking radiation, due to quantum effects near the event horizon. Over very long timescales, this radiation can cause black holes to evaporate. The question then becomes, what happens to the information that fell into the black hole? Does it disappear, or is it somehow preserved? Recent developments, including ideas involving holography and quantum entanglement, suggest that information may be encoded in subtle ways, perhaps on the boundary of the black hole, or in correlations within the radiation. While this does not directly confirm the creation of new universes, it highlights the complexity of black hole physics, and the possibility that our current understanding is incomplete. So the idea that black holes might lead to new universes, while speculative, is not entirely disconnected from ongoing research. It sits at the intersection of cosmology, quantum theory, and gravitational physics, and it offers a different way of thinking about the universe, not as a single, isolated entity, but as part of a larger process, where universes give rise to other universes, each with its own properties, each contributing to a broader pattern. There is something quietly compelling about this perspective. It introduces a kind of continuity, a sense that the universe we observe may be connected to others through processes that occur deep within black holes. It also provides a possible explanation for why the laws of physics take the form they do, not because they were fixed at the beginning, but because they have been shaped over many generations by a process of selection. Of course, this idea is still being explored. It is not yet confirmed, and it may not be complete, but it expands the range of possibilities. It shows that even at the larger scale, concepts like variation, selection, and evolution may have a role to play, and it reminds us that the universe, in all its complexity, may not just be a static system, but part of an ongoing, dynamic process, quietly unfolding across scales far beyond what we can directly observe. There comes a point in any scientific exploration where the questions begin to outpace the answers, not because the answers are impossible, but because the path toward them becomes less certain, less direct, and more dependent on ideas that have yet to be fully tested. In cosmology, that point lies close to the beginning, not the beginning we can describe with confidence, but the one that sits just beyond it. Up to a certain stage, our understanding is remarkably strong. We can measure the expansion of the universe. We can observe the cosmic microwave background. We can calculate the formation of light elements and trace the growth of structure across billions of years. These are not vague impressions. They are precise, supported by data, and consistent across independent observations. But as we move closer to the earliest moments, the clarity begins to soften. The models become more dependent on assumptions. The evidence becomes more indirect, and the questions themselves begin to change. One of the key concepts in this transition is the idea of an observational horizon. The observable universe is not the entire universe. It is the portion from which light has had time to reach us since the beginning of cosmic expansion. Because light travels at a finite speed, and because the universe has a finite age, there is a limit to how far we can see. This boundary is known as the cosmic horizon. Beyond it, there may be more universe, perhaps much more, but it is not accessible to observation. No signal from those regions can reach us, at least not within the current age of the universe. This is not a limitation of technology. Even with perfect instruments, the horizon remains. It is built into the structure of space-time itself, and it reminds us that our knowledge, while vast, is not unlimited. There are also limits that arise from the nature of measurement. At very small scales, quantum mechanics introduces fundamental uncertainty. As we discussed earlier, certain pairs of properties, such as position and momentum, cannot both be known with complete precision. This is not due to experimental error. It is a fundamental feature of reality. So even in principle, there are aspects of physical systems that cannot be determined exactly. At the largest scales, similar limitations appear in different forms. We can measure the cosmic microwave background with incredible precision, but we can only observe one universe, one realization of cosmic history. We cannot repeat the experiment. We cannot compare multiple universes directly. This introduces what is sometimes called cosmic variance, a limit on how precisely certain quantities can be known, simply because we have only one sample. These limits are not flaws in science. They are part of the framework within which science operates. They define the boundaries of what can be observed, measured, and tested. And within those boundaries, science works remarkably well. But beyond them, the situation becomes more subtle. This brings us to a deeper question. Are there aspects of the universe, particularly its ultimate origin, that may be fundamentally unknowable? This is not a question about current technology or current theories. It is a question about the nature of knowledge itself. In philosophy, this is known as epistemology, the study of what we can know and how we can know it. In cosmology, epistemological limits arise when we consider questions that may not be accessible to observation, even in principle. For example, if the universe emerged from a state that leaves no observable trace, then there may be no way to reconstruct that state from data. If multiple models predict the same observable outcomes, then distinguishing between them may be impossible. And if certain regions of the universe are permanently beyond our horizon, then their properties may remain unknown. This does not mean that inquiry should stop. Far from it. It means that science must carefully distinguish between questions that can be answered and those that may remain open. It also encourages the development of new methods, new ideas, and new ways of thinking. Throughout history, many questions once thought unanswerable have eventually yielded to investigation. The structure of atoms, the nature of light, the expansion of the universe itself. Each of these was once beyond reach and is now understood in detail, so it is possible that some of today's uncertainties will be resolved in the future. New theories, such as a complete theory of quantum gravity, may provide deeper insights. New observations, perhaps of gravitational waves from the early universe, may reveal previously hidden information. The boundaries of knowledge are not fixed. They shift as understanding grows, and yet it is also possible that some limits will remain, that certain aspects of the universe, particularly those related to its ultimate origin, may lie beyond what can be tested or observed. If that is the case, then the role of science is not to eliminate those questions, but to clarify them, to understand what can be known and what cannot, and to explore the space between. There is something quietly reassuring in this balance, because it means that science is not about having all the answers. It is about building a coherent picture, grounded in evidence and open to revision. It is about following the data wherever it leads, even if that path does not reach a final destination. So as we consider the beginning of the universe, we find ourselves at an edge. Not an edge in space, but an edge in understanding. A place where observation meets theory, where certainty gives way to possibility, and where questions remain, not as obstacles, but as invitations. Invitations to think more deeply, to explore more carefully, and to continue the search with curiosity, with patience, and with the recognition that the universe, in all its vastness, may always hold just a little more than we can fully grasp.